Welcome everybody at this first session of the GdR RO for Data Machine Learning and Optimization group of the GdR RO. Today we are pleased to hear a talk from Thibaut Vidal. So Thibaut is now a professor at CIRELT in Montreal. After doing his thesis in France and in Montreal, he has done several postdocs in MIT and in Austria before going to PUC-Rio, where he was a professor for a few years. And now it's fresh from this year. He's a professor at École Polytechnique Montréal. And among other things, Thibaut is very well known for his contributions to heuristics in routing. And I encourage you to look at his hybrid genetic search works and the great codes that are available on his GitHub pages. But today he's going to speak about something different, and we will be pleased to hear what he has done at the crossroad of optimization and machine learning on interpretable ML. Thibaut, you can start, please.
Fantastic. Hello, Axel. Hello, everyone. Thank you so much for inviting me today to give this seminar on tutorial. I will share my screen. So the topic of today will be about actually something fairly different from routing. It will be about combinatorial optimization and interpretable machine learning. So we have all seen the very quick rise of machine learning in a variety of contexts. It influences our trajectories as our researchers. And as I will try to demonstrate today, there is plenty of opportunities of very deep and interesting research in this area. So I'm a new professor here in Polytechnique Montréal. I have been also recently appointed as a Scale AI chair in data-driven supply chains. And you will perhaps hear of project of this chair over the next 5 years. I'm also a member of the CIRELT in Montréal and still advising my student also in PUC-Rio. So that's it. That's a lot of work that has been done partly in PUC-Rio and more recently also while I've been professor at Poly. So, well, when we look at machine learning, we have seen a gradual shift of the attention from original studies that were more about really classification performance, training, heavily focused on, let's say, state-of-the-art result on some benchmarks, and a shift that is much more towards interpretability, transparency, fairness, and so on. The reason is that if you look at most recent applications of machine learning, you see applications that closely impact humans. You see applications in medicine, you see applications in credit evaluation, in criminal justice. These are all cases where a wrong decision can heavily impact the lives of people. So one would even argue that in some of these applications, for example, criminal justice, the current models, they are not mature enough to be used. It seems to be particularly true. In other cases, they could be mature, but they need some control. So you want to know if some minority group has been disparaged by the algorithm. You want to know if there was some errors or some bias that came from the data and so on. And you want to not only take a decision, but explain those decisions. So as part of the project that I'm currently driving in the Scale AI ecosystem with the chair, one of the main targets of my current research is to meet both research lines between, let's say, state-of-the-art performance with optimization and machine learning and explainability. That's going to be the topic of today. So humans, they can be very biased in the way they work. You can lack fairness, lack justice from the data, also due to the algorithm. Even if you exclude sensitive attributes, for example, gender or race, the model may still be able to indirectly exploit these features by using proxies and other features that are heavily correlated. So it is actually extremely difficult to make sure that when you take decision on a data set that is large enough, the motivation of the decision is fair and not touching at sensitive data. So there has been a very large interest these days in better understanding the decision-making process in these algorithms. Two notions have very often appeared, and they are not interchangeable. There is the notion of interpretability, and there is the notion of explainability. So let me explain why they are different. Something that is interpretable is something of which you can understand the mechanism that lead to some decisions. So for example, if I give you a decision tree and I track the choices that are being taken within the decision tree, I can follow step by step how the decision was made. So it's easier for me to understand how this mechanism works. By design, interpretable models should also be transparent, because there is no way to have interpretability if you cannot see the internal workings of the model. Now, explainability is something that is quite more general. Explainability doesn't need to be always based on a transparent model. It only requires that you have some process in place to explain the decisions of the model. So actually, you could very well have a black box model of which you don't know the internals, but having a second algorithm on top, which is in charge of providing explanations. So in this talk, we are going to make a first part of, let's say, 20 minutes that reviews classical studies and methods in interpretable ML. And then I'm going to pinpoint, in connection to recent work, 3 specific applications where there is a lot to be gained by using combinatorial optimization in that context. So 2 of these papers and works have been already published, and the last one is a kind of work in progress that should soon appear as a report. Just some basic notations. We are going to consider a data set that is made of a set of samples, of n samples, where every I index refers to a sample. And we assume that the samples, they have been independently drawn from a distribution X, Y. And we want basically to learn how to predict Y based on X. So Y could be either a value in case of regression problem, or it could be a class in case of classification problem. Let's start a bit with very classical models that are qualified to be interpretable. Perhaps the simplest model of all is linear regression. You get a set of samples. You will try to minimize the square deviation of the error. And by using the coefficient that you obtain by doing this regression, you are able to issue new predictions for regression problems. This is extremely easy to comprehend because once you have calculated the regression fit, you can see the coefficient of each of the features that led to this regression. However, it has a number of limitations. First, there is a heavy assumption on the data for this to be statistically relevant. In particular, you are looking at data that should be linear, that should be issued from a normal distribution, and so on and so forth. The second thing has to do with correlation and collinearity between the variables. If you have 2 variables that are very, very heavily correlated, it could well happen that in the linear regression, you have a very large coefficient or positive coefficient in front of that variable that seems to indicate that this variable is quite important. And the second variable, even if it's quite similar, is just used to kind of correct the classification because it has minor differences with the first one. In that case, you may have very biased interpretation of which variables are important or not, just because of some noise or some small differences between some features. The other thing is that, well, the scope is fairly restricted. In many cases, you need to extend linear regression to some more general context. And for example, one way to do that is to use generalized linear models. There are other ways of also generalizing linear regression. You can simply operate a feature transformation. You can generate additional features. And in a very extreme way, if you want, you can generate, for example, using splines or a lot of feature extraction methods, generate sophisticated function of the data and include them in a fit, leading you to a more complex model that we call generalized additive models, GAMs. Okay. Now another model that is very classical and quite transparent in a sense and interpretable. This is the support vector machine model. So support vector machine is really designed for classification originally. The idea is that you have a set of points. Here I have two groups of points that are on my data. And I'm looking for a separating hyperplane, this one, which has the maximum margin between those points. Well, of course, this example is a very clean example. There is nothing bad going on, but you could have data points that are in the wrong side. This is permitted in support vector machine with hinge loss penalty. And in this case, you can still look for a separating hyperplane, and any sample that is in the wrong side will receive a penalty that's proportional to its distance from the opposite side of the margin. You can formulate that very simply as a linear program. You have a term that tries to minimize misclassification mistake that comes from this Xi variable here. And you have some linear constraint that basically impose you to be on the good side of the hyperplane or otherwise pay some penalty. Finally, you have a regularization term in this objective that aim to minimize the amplitude of the coefficient of the hyperplane. Even if it's not very intuitive at first glimpse, the effect of this regularization coefficient is that it will force the model to maximize the margin due to the combined effect of this regularization with the fact that you ask for 1 unit of margin here. And that has led to very successful applications with methods that are fairly explainable and interpretable. On the other hand, support vector machine in its basic form is not very often included in the class of interpretable model directly. The reason is that it's not very common to use the linear support vector machine formulation in practice. The most classical application case of support vector machine is in combination with kernels, which are ways of projecting the current data in feature space of higher dimension. Because when you do that, you have more opportunity to fit the data and to separate it, leading to, in practice, to separation that do not look linear in the original space. The problem is that with the kernel transformation, you largely lose your interpretability. Okay, another very classic class of interpretable model are decision trees. So decision trees, they consist of a tree in which the internal nodes of the tree, they represent conditions that you can test and that usually consider only one feature, one attribute of the data points, but there exists generalization that involves splits that are multivariate, that involve several features together. In the simplest form, you will test, for example, well, is my nucleus the size that is greater or small or equal than 3.5. If this is true, I go to the left. If not, if you are strictly greater, you go to the right. So once this is trained, it is very easy to follow the decision process within a decision tree. Just go from the root, you pass from the root to the leaves, and you are going to get your final class. Training a decision tree is done usually in a way that is a form of greedy algorithm, which will progressively create the splits in such a way that it divides the best the data and maximize the information gain at each step. These models are very interpretable, but they have a few bad tendencies. The first is that the performance is not always that great. That really depends on the structure of the problem. The second thing is that it's sometimes difficult to know when to stop when you train a decision tree. If you should split further or just stop there. So there is some calibration that is needed. One way to get better performance with decision tree is to use them collectively, not having just one single decision tree, but having a forest that includes, let's say, hundreds of decision trees together. When you do that, you will introduce some randomization in the way you generate the decision trees. Typically, one way to do that is to only consider half of the features in a random fashion whenever you choose to split something at the training stage, and also not training on the entire subset of the data, each tree. This means that in practice, you are able to generate a number of trees that all give you different views on the problem with a classification for your task, but that collectively can be used to find a better answer. So when you have many trees, the usual thing is to just look at the majority vote, which class is voted to be the most, the best for the forest. So all these models, they are transparent and interpretable by design. You can see in many cases the flow of the decision process in a way that is quite visual. And some of them allow to comprehend some of the interaction between the features. However, they don't very often attain the state of the art. I mean, if linear regression was so efficient in practice, everybody would be using it, but unfortunately, that's not the case. So it heavily depends on key assumption of the data, and it also may lack stability and robustness in some cases, in the sense that a small change in one of the data points in the training set can have a big impact on the construction of the classifier or the prediction model. And also in terms of robustness, sometimes just small change in the test sample can very heavily impact the decision. Now I'm going to talk a bit more about explanation methods. So explanation methods, they are usually designed for models that are more sophisticated than that. So I briefly described tree ensembles, the fact that if you want to get better decision, you may make decision based on many trees together. Another class of models, which is quite difficult actually to interpret directly, is the class of neural networks, and especially deep neural networks. And those are definitely difficult to comprehend just by looking at the weight and the networks. You cannot so easily say what is going on. So in those cases, the methods that are used are more about explaining rather than directly interpreting the decision flow. There is also a situation where you don't even know the internals of the prediction model. So you cannot look inside the black box to tell, well, those are the decisions, those are the way, this is why these decisions have been taken. The reason for using black box model is that in some application, for example, for application involving safety or perhaps cryptography or application that you basically don't want to see reverse engineer it, you don't want anyone to reverse engineer them, then you may have an interest to use a black box, or also to protect data. So in that case, well, you will need some algorithm to explain those models. Perhaps the simplest explanation method is the feature importance measures. So the first reflex that you may have when you look at the data on the model is to ask, well, how much each feature of the data contributes to the prediction. So one way of doing that is basically to take this feature in the data, to shuffle the values of this feature among the different training example, and see how much it impacted the prediction performance. Here, there is not a clear agreement on whether you should retrain or not when you do that. Some people do it, some people don't do it. That really depends on the context. But the idea is that features which strongly degrades the prediction performance when you remove it is an important feature. So you can make an interpretation, okay, if I remove that attribute that was kind of sensible attribute, it becomes much worse. That means that my model is heavily based on this attribute. It should not be the case. So let's see what's going on with the model. There is, however, shortcomings with this kind of feature importance method. One of them is that when you have, for example, features that are identical, for example, in an extreme case, well, if you shuffle one of these features, the other is still there. So you will have the impression that it contributes to nothing. However, if you were to remove both of the copy of the features at the same time, you would be able to see that this feature was very important. So that's a very big limitation of the current feature importance method. They look at individual importance of the features. They are not giving a view of features, for example, from a group viewpoint that may be much more relevant when you have big correlations. Another way of calculating feature importance is grounded on cooperative game theory, and it's called SHAP. That is generally an application of Shapley values. The idea is that you make an analogy between the features and some players and the game where the surplus is the prediction. The Shapley values can be calculated in some contexts, and that allow you to attribute some weight to the different features. However, this model also has some shortcomings. The first thing is that, contrary to the previous case where you had, for example, two heavily correlated features that are basically no feature importance, in that case, the contribution of the feature, they get distributed among features that are heavily correlated. So it kind of dilutes the contribution of individual features that are important, but that are kind of together as a group. Boom. Beyond explanation methods that are based on feature analysis, you have some methods that are designed to kind of imitate a complex model with something that is simpler. This has been called sometimes global surrogate. So the simplest form of doing that is the following. I have already a model on a predictor that is trained. I want to understand how it works. So the thing I will do is to feed a lot of the data to this predictor, get the prediction, and this data on the associated prediction will form a new data set on which I can fit a different model. That's basically making a model on top of a model. If you choose the second model to be something more interpretable, then you can claim to have some interpretability. However, it has very heavy shortcomings. The first thing is that you had already one model to debug. Now you have two. The second thing is, if you have some inaccuracy on some discrepancy with the expected result, you may need to locate whether this was due to the first model that you had, the original model, or the surrogate model, because it can come from both. One of the topics that I'm going to present a bit later today is related to global surrogate models. Actually, that's a specialized technique that applies to random forest and that just generates a single decision tree that has the same prediction function as a random forest. The good thing is that with some mathematical optimization, you can prove that both models have the same behavior. So you are not really creating a surrogate model in that case. You are creating something that is identical in terms of its prediction function everywhere, but that has a different structure, a single tree compared to random forest, for example. Another very classical, which used in a large number of contexts, is the LIME, which is local interpretable model agnostic explanations. So LIME, it is kind of a specialization of global surrogate model, except that it's focused on a specific data point, and it tries to give an explanation that is localized around this data point. So the main difference between LIME and global surrogate models is the way the data is generated to train the surrogate model. You will basically take a data point. So you had maybe a complex function that was like this with the data point that were on both sides. And you want to understand how is the prediction on this data point that is here. So you will look at this region. You will create new data points to analyze the behavior of this model on this data point. And based on these new data points, you will create a surrogate model that could be, for example, a linear separator or linear regression to understand exactly locally how the model or the frontier of decision is, for example. That's the goal of LIME. And there is very specific strategies that have been designed to know how to weight the data set, to have samples that are close to the data point that you want to explain. And there is a number of applications to computer vision application, different specialized version of this method. The last type of explanation algorithm is called counterfactual explanations. So currently we were either talking of understanding the importance of some features or simplifying somehow the model either locally or globally using some surrogate models. Counterfactual explanation, they are more related to kind of negotiation perspective. You ask for a credit and someone tells you, no, sorry, with your data, we will not give you that credit. The first reflex, if you were into bank and that somebody tells you no, would be you asking why I didn't get this credit. I have good, I have a good salary. I asking for a good duration. Why my case is not working out? And the person that denied you the credit will say, well, it's because of this. Well, counterfactual explanation is exactly the process of giving this because. So when you try to explain to someone because of this, basically what you do in your mind is that you look at the current data point, which is, well, you put it in red because it was not accepted. And you look at the closest point that for you would work out for your task. And basically you will tell the difference between those 2 points. Of course, you have interest in giving an explanation that is involving a green data point that is as close as possible to the red data point, because the difference between these 2 points is the actions that you need to take. So if there is a small distance, that means you don't need that many actions to achieve your goal. So a good counterfactual explanation is an explanation, a data point that is very close to the original data. The problem is that, well, the optimization model related to the search of a counterfactual explanation is not something so trivial to solve in many contexts. First, it's bound to a notion of distance, because we are looking at explanations that are close to the original data. And there is many variation of distance metrics, penalty function, or regularization term that you can use here. The second thing is you need to achieve the target prediction with the green data point. And this is where the crux of the search algorithm is. If the f, the predictor function, is something simple, that is smooth, that you can get a gradient, that is convex, Well, everything perfect. Just do a gradient descent and you get a good counterfactual explanation. If you have something that is much more complex, for example, a random forest, then you start to have combinatorial behaviors and you may need very sophisticated techniques to find a good counterfactual explanation. We're going to talk of that a bit more in the remainder of this talk. So some advantages of explanation method. You don't need to know exactly all the internals of a black box model. There is many explanation method that will work even just assuming that you have an oracle that gives you the prediction. However, they put an additional layer of complexity on top of a model that was already complex. So in a sense, you are making things worse. You wanted to understand a process. Now you have a process that's even worse because you have the prediction process and you have the explanation process, and both of them could have some shortcomings. So that's it for now. This is a very, very short tour the horizon of interpretability and explainability. We are 36 minutes. I will do in 15 minutes more the first work that I wanted to highlight, and then I will make a session of questions and a small break for you. So the first work that I want to show to you is called Born Again Tree Ensembles. That's a work we did last year and that was submitted and accepted in ICML. And the goal of this work is to transform a random forest, which is something that we would say is quite complex because you have the collective decision of many trees into a single tree, just one. And I want this tree to be as small as possible, and I want the behavior to remain the same. So I explained a bit a number of techniques for surrogate models and explanation and simplification of models. I don't want to dig that much again into the literature, but here in the slides, you have more detailed citations to some of these specific works. So when you want to simplify random forest, one of the way of doing it is to, for example, prune some weak learners by removing, for example, some trees in the forest. Another way is to replace the tree ensemble by a single tree, which is what we are going to do in this work. And there is a number of other techniques that are here. Also, simplification and pruning is not only restricted to tree ensemble. You see that also applied to neural networks and a number of other prediction models. Let's continue. So in mathematical terms, what are you looking at? We are looking at a prediction function that comes from a random forest. And I want to create a tree, a single tree, that has the same prediction function, though, so we call that to be faithful. And we want this tree to be as small as possible. So it should be the smallest in terms either of number of leaves or depth, for example. Just from a geometric perspective, in a very, very simple 2D case, you can think of the process of training a born-again tree, the single decision tree that imitates the forest, and this is the forest, as a few steps, actually. Every tree in the original forest, it corresponds to a kind of map of the feature space in which every split corresponds to the hyperplane and every leaf corresponds to one of the final class that is in the tree. It has a very strong similarity actually with things that we know in cutting and packing, like these guillotine cut problems, and things that do this kind of hierarchical splits. But this is for one tree. If you have many trees, you have many maps. And if you look at the collective decision, which is the majority vote of these predictors, you basically can represent the prediction function as a function that is piecewise constant and in which every little cell that have been represented here by overlaying the different maps as just a single possible prediction associated. We are talking here of classification problems, so prediction are just classes. So terminology, this will be called a cell, and a rectangular set of cells here in 2D, but a hyperrectangle in higher dimension is going to be called a region. And the region can be entirely characterized by two cells, the bottom left and the top right. And well, if I was able to write this map of all possible decisions within the filter space, I could be interested to use this map and build finally a decision tree that represents this behavior. So we are combinatorial optimization people. If we look a bit at how it looks like, it's really like if I take this map, it gives me kind of non-convex regions, and I need to find again a good set of cuts that are guillotine cuts in such a way that the depth of the cuts is limited if you want to limit the depth of the tree. And the resulting regions, they are homogeneous in terms of their prediction and convex. That's what we are trying to do. There is two issues. The first thing is this map here, it looks nice on 2D because it's a very tiny example. But in a high dimensional space, if you have 50 features, it's impossible. Just even to write it down, it's going to be totally intractable because the number of cells grows as the product of the number of splits of each feature. So that's totally intractable. And even if you're able to represent the map, constructing this optimal bounding gain tree is really not straightforward. But well, let's try to do that and see where we go. So it's not a surprise that this problem of optimally creating a bounding gain tree is NP hard for any meaningful objective that involves like optimizing depth, number of leaves, or hierarchy of those two. Actually, even verifying that a given solution has the same prediction function is NP complete, is a decision problem. So the first thing you can do when you have something that is well structured like this with regions and cells is to go for a dynamic program. You can easily express the state space because you can consider all regions and try for every region to characterize the smallest decision tree that faithfully represents the random forest within that region. That's what we are going to do. The phi function here is going to calculate the objective function of the best decision tree for that region. Obviously, if that region is homogeneous in the sense that all samples within the region return the same function, then the complexity, the depth of this tree is zero, just a class, final node. Otherwise, well, there are some different classes within the region. There will be needed a split somewhere, and you are going to look at all features, all possible levels for a split, add one split, and get the size of the left child and right child. That's going to give you the size of the decision tree that you create by doing this. So you can really easily express the solution of this problem as a dynamic program. There is two issues with this dynamic program. The first thing is that even testing the base case for regions that are non-trivial is difficult. And the second thing is that you have a lot of recursions. You are going to very quickly increase the number of states and open a lot of recursions. Well, there is ways to handle some of these issues. The first thing is that you can integrate the base case testing within the memory of the dynamic program, which saves you a lot of time in many situations. And there is also tricks to avoid opening too many recursions. These tricks, they are based on very simple monotonicity properties of the problem. If I give you, for example, this prediction function, where you have in the map, those are returned as 1, class 1, and these one are returned as 0. So I'm looking for the best decision tree that captures the behavior. Suppose that I have already tested this split and I know that the optimal decision tree of the left is a depth of 2 and the optimal decision tree on the right has a depth of 1. Does it make, oh, well, this means that you end up with something that has one node on top and a depth of 2 on the left and depth of 1 on the right, which is a decision tree that has a depth of 3. So this is an incumbent solution here that has depth of 3. Does it make sense to search on the right? The reason is no, because if you go on the right, one thing is certain, that value 2 here, it will not decrease because you're looking at a larger region. And it's pretty obvious that it's monotonic. It's very easy to prove in mathematical terms. If you have a larger region, I know that the best decision tree for the left part is going to be at least 2 or more. So since 2 was creating the maximum of both sides, regardless of what I do, if I try to split on the right, I will not get anything better than 3. This also works in reverse order. If you had 1 and 2, there is no need to go on the left. And the sweet case is when you have 1 on 1, because you can stop looking at split for these features. You know that there is no possible feature splitting level that could do better than that. This is just the algorithm, not something overly complicated. Actually, in C++, if you look at the GitHub repository, it just fits in 100 lines, basically. You cool the memory to remember if you already got the result for this region. Use some bounds that can help speeding up some process. You test every feature and you do kind of binary search due to the monotonicity property that I just gave. You start from the middle, and if you attain equality, you stop. If you have one side that is greater than the other, then you know that you need to search on the other side. You calculate within each call the recursive call to the DP on both sides. You update some bounds based on this, and that's it. That's how it goes. It looks very simple, but this algorithm has been the result of a lot of testing. In the beginning, we used, for example, a mathematical model within the DP, and we tried different combinations with MIP in order to do something better, and we didn't get much success. Our most successful approach was really like DP with the fastest possible iteration speed, something that is almost linear constant time for each recursion. Nevertheless, you can get very interesting results even with this simple algorithm. The first thing that you want to know is, well, if I'm now able to look at a random forest and get a single tree that represented, how does this single tree look like? Is it something very complex? Is it something that I can use? What is the benefit of it? And the second thing is, well, to what extent can we push this method? Can it go very far, or is it something that will quickly just explode in my hands? We applied it to different data sets. In that case, the largest number of features that we did with the DP was 17. And there has been some data preparation that's quite classic. This is the behavior of the algorithm as a function of the number of samples. Actually, here we see that it decreases, but usually the number of samples doesn't really matter, because what matters in the algorithm for this DP is the number of cells. That is basically the number of splits in the forest. So it's not a surprise that when you have a large number of features, the number of cells grows exponentially, and you see that the computational time of the DP starts to grow quite quickly. It's a bit the same with the number of trees, however, to a smaller extent. It's just that when you have more trees, you have more split level. When you look at the overall forest, there is a larger number of split levels. So you end up having more cells. But the effect is not as acute as just directly increasing the number of features. First surprise was that when we took a random forest that has just 10 trees, and every tree has a depth of 3, which means that there is basically 8 leaves on the bottom of the trees. Well, these trees originally, they don't have much complexity. They are just 10 trees with like eight terminal nodes. We were expecting to get, let's say, 80 nodes in the born-again tree. But that was not the case. We end up with optimal born-again tree that, for example, for the minimization of the number of leaves, had sometimes hundreds of leaves. And we were wondering why it's necessary when you try to imitate a random forest with a single tree, you end up in some cases to have much more leaves than you would actually expect. Well, there is a logic to that. The first thing is that it's very easy to generate bad cases where the number of leaves of a born-again tree grows as the product of the number of trees of the original trees in the random forest. Remember that the behavior of random forest is something combinatorial. The decision, they come from the combination of decision of many trees. And that combinatorial behavior clearly translates into the structure of the tree that we build based on the original random forest. But there is a second reason for that. And this reason is also quite easy to understand. That when you look at a feature space, very often you end up with a situation like this, where you have data points that are here and here, for example, but there is none here, just because some features values, they are mutually exclusive. But if you look at the behavior of a random forest in this feature space, it has a complex behavior here and here with a prediction function that is a bit complex to write. But its prediction function also exists here. Even if there will be never any data point here, the prediction function exists. It's just that there is never any sample that will go through this. And when we do the born-again tree, we also try to reproduce this part of the prediction function, which is a part of the prediction function that is useless. So the thing that you don't want to do when you create the born-again tree is to reproduce the full complexity of the model, including in regions of the feature space that are not plausible, that have absolutely no meaning with regards to the original thing. So one way to do that is just to apply some very simple pruning techniques that can be done as a post-processing step. And that consists in looking whether you have some samples that pass through all nodes of the born-again tree. If you don't have samples that pass through it, well, then you can just cut the branch. Then you end up with something simpler. In the current code, we did that as a post-processing. But in future works, and we are working on an extension of this model, I strongly suggest that this to be done directly within the GPU to avoid generating something extremely complex and then having to simplify it. The magic happens with post-pruning. Instead of having those large number of leaves in the born-again trees, we end up with a number of leaves that is much smaller, and that actually becomes comparable or smaller to the total number of leaves in the original random forest. So we really get the target of something that is more interpretable because it has less leaves. It is a single tree. I can just look at a single trajectory within it. It's also faster, by the way, if you look at embedded system that has very fast response time and the prediction step, it's better for you to have a single tree instead of many. It's much faster for prediction. So there is a number of advantages to using the born-again tree. And well, before pruning, mathematically, we can prove that the accuracy of the model on out of sample is going to be the same anyway, because mathematically we have proven that the prediction function is the same. It's not so true when you do pruning. It can still remove some regions that, well, looking at the training data, this region didn't look useful, but on test data, this region could have had an influence. So we tested it to see whether we had any degradation of performance on the out of sample test set, and we did not notice anything big or very significant. For all purposes, the pruning did not really modify much the behavior of the classifier. Research perspectives, well, this is already done We used DP because we wanted something optimum to really like be able to look at how these born again trees are. Wanted to have something, a firm ground for the analysis. You can keep the faithfulness, that is, you can keep the assumption that this is identical prediction behavior, but for example, relax the optimality requirement. That is, at the construction of the born again tree, you don't impose to always find the optimum. If you do that, you don't need always DP anymore. You can do a good combination of heuristics with some kind of bounding and integer programming techniques for testing faithfulness. And in that case, you can scale up the concept to much larger data sets. We already tested it for 50 features, but it's really a question of implementation at some point. I believe that we will be able to go higher than that in the near future. And with the heuristics, we got born again trees that were like 20% bigger, but this doesn't make much difference when you look at practical application of those models. That's it. That's the first part of the talk. I don't want to extend that much more. I will leave you now some time for questions. At the end, we are not a huge number of participants, so I believe that question could be done either through the chat, or also anyone could go on the video and directly ask. Okay, thank you a lot for your attention. Hello, question, Wento? Is my sound right? Okay, so can you allow to turn on mic? So I have the controls in this. Yes. Let me see. Jerome has, okay, Jerome Malik. Let's wait a little for Jerome to arrive. Okay, then I will take on some questions directly on the chat, and as soon as the microphone is liberated, we can have direct questioning. Limitation of born again. Well, there is limitation, obviously. If you look for the optimal solution algorithm, since it's based on dynamic programming, it basically explodes when you have a large number of features. So as long as you go with that, if you go with DP, you are going to be limited in terms of the data. As soon as you go to a heuristic that relaxes the optimality assumption on the size of the resulting classifiers, you can already go towards much more tractability, but you are still limited by the fact that you impose to be exactly the same behavior from the prediction perspective. So once again, if you want to go even higher in terms of scalability on features, you may need to relax this other assumption. And relaxing faithfulness require you to have a metric to tell to what level you want to imitate the original model, what is the precision needed, and things like that. So it's really a question of what is your goal and how to develop the algorithm to fulfill them. But there is plenty of space to improve those algorithms, clearly.
How would you formulate the learning objective in that case? And what happens if you restrict yourselves to given depth trees, in the sense that you don't want more than a given depth, so you must be approximate, and so which objective could you give in that case?
So the first thing that we tried, there is a master student working on that in PUC-Rio, was to, for example, well, first straightforward approach would be to reproduce the behavior for X% of the cells. That's straightforward. The problem is that cells, it could be big or large. So it's not a very good objective in terms of faithfulness. So you need sometimes to have different ways to tell you what cells are important in the training of the born again tree. Another way is, for example, to make a model of your data, for example, as a Gaussian mixture. And if you have represented your data as a Gaussian mixture, you may try to get, for example, 99% of the mixture that is faithful when you train the born again tree. This is a bit more sophisticated. It requires more tricks when you do the training. And also combining the tree size can be done in that context. Of course, the algorithm will change quite a bit when you do that. Yeah, Zachary, you are totally right. This is because originally when we did the GP, we didn't realize that problem, that we are basically reproducing the behavior everywhere. We did this as a post-processing, but we could have gained a lot of time by removing it directly during the DP. I'm, however, worried that the DP could kind of exploit it a little because it will optimize on that. It will not just be used once as a post-processing. So I don't know if there could be any side effect to integrating that directly in the DP. That's not something that I have tried yet, but this is part of my my research agenda also with the relaxation of the faithfulness and other work also that relates to using the techniques that is known as isolation forest to tell which region of the search space of the filter space are really worth it reproducing, worth reproducing. Thanks a lot. Any other question? We can take a 2 minutes just to talk of anything or nothing, because it's a long monologue if I do just 4 talks consecutively. So do you see in the near future that explainable AI will have libraries? Oh, yeah, that would be amazing. I mean, there is already a number of libraries of code that have been done to for explainable AI, but the application of explainable AI goes in such a broad range of application context on the broad range of data size and data types that usually users are quite scared of integrating complex models that have, for example, some parts that would be combinatorial or some NP-hard subproblem at any place, because they know that it would blow up in some situations that it may need to be used sparingly. So if you integrate that within a very widespread code library, you may run the risk of having a lot of users complaining, oh, your super nice models, I try to apply it to my data with 10,000 columns and it just doesn't work. That's the problem. I mean, if you want something that is really like easy to use by the public, and then everyone usually want to restrain to very low complexity, stochastic gradient, linear complexity, log linear complexity, all the algorithms that you can do that really extend well to a lot of data. And currently that doesn't include born again trees, for example, with the assumptions that we have taken.
Did you use it as a computational subroutine in other algorithms? Because just to simplify large forest, where you need when you need to have computationally efficient algorithm.
So we are working on a number of projects that are applications of this concept. One thing that has been done in connection with Maximilian Schiffer and other colleagues of him was to apply this to the data of Deutsche Bahn. So Deutsche Bahn has recourse systems in place when there is disruptions on the lines. And you don't want always to look at the entire system to choose a recourse when there is something that is quite standard. For example, a train is breaking down, you need to put a different track or a different train. There is a number of recourse actions that are very systematic and that can be learned. So Deutsche Bahn has already a learning algorithm for that, and it uses random forest to some extent. The only problem is that the random forests are very large and they are very difficult to understand why did this kind of recourse action. So one of the current action item and ongoing work that we have is to just pass these random forests through our born again tree in order to give them back a single tree that does the same job. And so for the user, it's much more interesting to be able to track the decision within a single tree to see how these recourse choices they have been made. There is also a number of other applications that have been discussed and that we are currently exploring. For example, looking at destination prediction in some GPS systems, and probably there is a lot of use cases that involve in which this kind of algorithm is really useful. Okay, I think I could suggest that I proceed to the last two small sections of the talk. This should not be as long as the first two, so perhaps in 35 minutes we are done and we can have a complete set of final questions. Is it a good approach?
Yes, perfect. Please go on.
Okay, that's great. So I'll continue. So back to the slides. Oh, before I continue, I just wanted to show you one little thing. We have, if you want, a Jupyter notebook that you can use. Can you see my screen now? Illustrated example. Well, I will put my screen, it's easier. So we have this. Just go in the GitHub. You get the born again trees repository. You go in docs and you look at the illustrative example. Okay. And this is a Jupyter notebook that you can run. And it directly applies the algorithm on data sets for which we have already pre-calculated the random forest for you. So there is very little implementation effort to do. You can look at the original random forest, for example, here. So that's the original forest. You see it has a lot of different features that are used in different trees. And this is the resulting born again tree after pruning. So that's what you get by applying our method. So arguably you can say, well, this is a bit more deep. So it may be a bit more difficult to track. But really, like looking at all combination of decision is not something easy when you look at a forest. I tried myself and I really have a hard time grasping how the prediction works when I'm looking at the forest directly. So all is there. Feel free to use it. We put a lot of codes actually in that repository. I try to centralize all my open source codes on my GitHub repository, which is now related to the chair, and also with work that I do with my collaborator, for example, Axel and other people, we try to put them in the same place. So, okay, I will go back to the seminar slides. We were on the conclusion of the born again tree. I'm going to go to the next topic that is about contour factor explanation this time, okay? So, well, I already explained a bit what is a contour factor explanation, what it is about, and the fact that when you have critical decision to make, you really need to explain those decisions. So credit allocation, the worst thing was recently when they did this analysis of bail decision algorithm that would decide whether or not some people could be released or not from jail based on their data. And they realized that there was heavy bias in these algorithms. So that has really triggered a lot of backlash on the machine learning community, but also stimulated a lot the study of interpretable methods to avoid this kind of situation. So what is counterfactual search? So I give you an initial point that is X hat here. And unfortunately, this X hat is not with the desired class. It has not been classified as a successful applicant or a successful credit. So you want to know why, and you want to know especially what can I do to change the outcome of this decision. So you are looking at a new data for you. So suppose I try to get a bit more salary, or I try to get a credit that is a bit longer in time. So I want to change my data in such a way that the prediction on my data reaches the class that I'm desiring to reach. And I'm also limiting this new example that I create, my new data point, to be within a polytope. And this polytope, I just put it as the intersection of two things, which is XP and XA. This relates to the two different concepts. XP is the polytope of plausible data points, that basically data points that make sense. And XA is the polytope of data points that are actionable, that is, that I have a chance to reach from my current state. So, well, there has been works that relate on counterfactual explanation, mainly from 2016, 2017 onwards. And the first paper that has been published by Vashter et al., a different reference, it was fairly simple. It was just, okay, well, to find a good counterfactual search, just generate some points within nearby your sample. Just by iterative sampling, you will be able to find a good explanation. Or, for example, okay, if the model is differentiable, if your prediction function is convex and differentiable, just look at a gradient, do a gradient descent, and you will find a good explanation. So that indeed works in a number of contexts, namely when you have models that are very well behaved. But if you look at tree ensembles, it totally is breakdowns, because tree ensembles, first, they don't have a gradient. You could try to simulate a gradient in a random forest, but it's not an easy thing to define. Second thing, they are totally piecewise constant and nonlinear and non-convex. You just cannot successfully find a good counterfactual explanation by something like a local optimization of this type. So finding good counterfactual explanation in tree ensembles, it has been raised as a big challenge in the literature and has been studied in quite a few works. The first works that we found, they were heuristics. So they consisted in tweaking the value of some features in a way that, well, it changes the path into a tree. The problem is that if you do that within a given tree, it may allow you to have one more tree that predicts the desired class, but it may totally change the behavior on the other trees. So there is no guarantee that tweaking a single feature in any of the branch of any of the forests will even return you a viable counterfactual explanation that achieves the desired class. And beyond the actual success or not of the method, even if it succeeds, it is not guaranteed at all to find an explanation that is nearby the original point. So we did experiments, and we observed that sometimes it would overshoot the actions needed to achieve the desired class by up to 30 times. So instead of telling you, well, your credit is denied because you need a salary that is $200 more, it asks for $6,000 more. That would be what happens in practice. So you may ask the following: is it fair and transparent to do that? I mean, if I give you counterfactual explanations that are highly unstable, that totally overshoot what you need to do, is it a real good recommendation? Is it something that is exploitable? I'm not certain. And since it's a heuristic, it can heavily depend on the initial point. So it depends on the subject. It can depend on the subject group, And we are back to the eternal question about, well, the fairness of all the methods that we designed for decision making. So in my opinion, the more we progress in time, the more heuristic explanations are going to become problematic. At least we should progress towards very, very stable and high performance heuristic, or we should even try to achieve optimality in that case. So the goal of this talk is to show you some opportunity of mixed integer programming designed for the search of counterfactual explanations in tree ensembles. There is a number of benefits that we know as OR people in going towards a MILP approach. The first thing is that the MILP approach, it is very flexible. So if tomorrow you need to integrate an additional constraint, and there is a lot of possible constraints that are useful in the domain of counterfactual explanation, well, you're able to do that. And you can do that by seamlessly embedding a new constraint in your model, and in most cases, it will just work. And second, well, we will see that it's possible to find optimal explanation within seconds for fairly large data sets, actually. So let's look at this. Well, this is basic content about what is a mixed integer program. So a mixed integer program is a problem that's represented as a set of linear equations in which we have some variables restricted to the integer domain. And this is subject to an objective that could be either, for example, linear, quadratic, convex, measuring how it's difficult to act on the different features. And we are going to solve that with one of our favorite solvers, which is GdR. Our model, it has a number of good characteristics. The first thing is that it has much fewer integer variables than previous models that have been designed in previous works, and it has a better linear relaxation. We designed this model to apply to different data sets that have, for example, numerical, ordinal, categorical, and binary features. And this works with a lot of objective, L0, L1, L2 extension of this objective, like Mahalanobis distance and so on. And more importantly, it can be very well extended to integrate actionability and possibility constraints. So how we do to search for a counterfactual explanation in a tree ensemble? Well, the first thing is that within the mathematical model, you will need to represent the flow of the samples in each individual trees. So for every tree that is in T, we are going to know whether we are going left and right in each node and in each layer. So what we did was to integrate a lambda variable for every tree on every decision layer that tells you whether it goes left, in that case 0, or if it goes right, in that case is 1. This variable is integer. So we have a number of variables that's proportional to the sum of the depths of the trees in the ensemble. And that's actually the only variable that needs to be integer in the entire model. The second thing is we need to connect the value of these variables with the actual left or right branches on each individual node of the tree. So this time we are going to put a variable y for every node. And this y is going to be connected to the lambda in such a way that it fulfills its definition. That is basically, if I'm in a node and I go left, it takes 0. You can prove that the integrality of the lambda implies the integrality of the y. So that's enough to represent the flow of the samples within every tree. Of course, if you do that, there is no connection between the flow of the samples. So there is no feature related to this flow. You have to somehow connect this flow together and see that they actually correspond to feature choices that are meaningful. We do that by different types of constraints for different types of features. So the first type that I'm going to talk is about numerical features. Instead of directly representing numerical features as a continuous variable, which would be quite problematic because it would require a kind of big M or logical constraint to link them with the branch choices. We have decided to decompose the value of the feature into different slices. So basically, as x1 goes from 0 to 1.0, it can reach 2 different thresholds. On these 2 different thresholds, they correspond to 2 different splits that exist in the forest. And basically, as x1 goes from 0.0 to 0.4, actually what will fill up is the variable mu01 that is written here on the model. And as soon as it gets 1, that means that x1 reached the value 0.4. And then while it goes from 0.4 to 0.6, then you will have this variable that will fill up to 1, and so on and so forth. So the structure of this mu variable, this is something like some kind called an ordered simplex. It allows us to have a very direct representation of the features, also with another constraint that is quite sparse. You don't have many terms in the matrix. And the good thing is that this mu variable, you can directly connect them with the splitting decision in the trees. So basically, if you take a left side here, you may need to make sure that this variable here, the mu11 and mu12, they are set to 0. So they are going to be 0 if you take the left side here. And this is done basically simply by bounding the mu by either the y or the 1 minus y corresponding to the case. And because there is this order on the mu variable, you just basically write a constraint between one y variable and one mu. So those are very, very sparse constraints. The other thing that is very practical with this representation is that it doesn't choose a big M, it doesn't choose any logical constraints, and the mu can actually be relaxed between 0 and 1. So you don't even need to impose integrality on those variables. And the good thing is that if you, for example, put additional plausibility or actionability constraints that are forming a polytope, you can find mu that are fractional, that are between 0 and 1, that correspond, for example, to a corner of the plausibility polytope. That totally works out with the rest of the decision model. Okay, other features, well, they have also very simple representations. For example, categorical features are quite straightforward to represent. Again, you can relax the 0, 1 status of this variable, and the same for binary features. There is a last class of features, that is ordinal features. So ordinal features is like, in a data set, you have like low, medium, good. Those are 3 ordinal scales. They have an order, but there is nothing that exists that is a meaningful concept between, for example, low and medium. So the open interval between 0 and 1 has no meaning. In that case, specifically for ordinal features, we have been using integer variables to represent them properly. You can put an objective on top of that. And well, the first thing that you can do is, if you have binary, categorical, or ordinal features, basically you have discrete values of those features that can be used for the objective function. You can put any weight in the objective function that can be feature dependent, level dependent, and it will work out. For continuous numerical features, one of the best way to proceed is to connect the objective as something that is a piecewise linear function of the mu variables that we have used previously. And this will work out very well for the L1 norm. Actually, it also works with the L2 norm. If you assume that the value will always be at the extremities of the intervals. Otherwise, you can also directly rely on the xi expressed as a sum of the mu variable if you want something more sophisticated. You can also express quite easily the L0 objective and many other variations of objective. That's not a problem. Finally, the thing that you want to do is really make sure that the model express the desired prediction. So you will do that by using the y variable that will basically permit you to count how many of those trees arrive to the leaf of the desired class. Okay, that's it. We put in the paper a number of discussions that relate to the integration of additional important consideration in the model. For example, in many cases, there is features that you will not be able to change. For example, my gender, I'm not going to change it to get a credit. There are features that are always monotonic. So my age is only going to increase unless I find a time machine somehow. You need to put this restriction when you look at counterfactual explanation, otherwise you run the risk of finding explanations that are absolutely useless. So that really is what we define as the actionability polytope. There are things that are just not actionable or are actionable in a way that's monotonic. Another thing that is important when you look at counterfactual explanation is that you cannot just look at features independently. There are changes to some features that imply other change in other features, simply because the features, they are correlated or linearly related together, or maybe there is logical implications between them. And the very good thing with a mixed integral program approach for counterfactual explanations is that you can very easily embed those relations. And finally, you can also put resource constraints. For example, suppose that changes in some features, they require some resource, like time. It takes me time to change my, I don't know, my salary or whatever. It's quite easy to put that actually in the model that we define. So you can do counterfactual explanation subject to resource constraint, plausibility and actionability constraint. That's really something very extensible. Okay, we tested that on a number of data sets. This time the data sets are much larger than in the previous case. They have like up to 57 features. We have 39,000 points, and they are related to, again, a number of important applications. Again, you can find everything on Git if you want to test the algorithm. We were very surprised by the performance of the MILP approach for counterfactual explanation. Gulobi is very efficient at solving this kind of model. It's really because it's a kind of compatibility model between it looks almost like a tree site in a sense. So even in the most complex data set, we never exceeded 10 seconds, and usually it was between 0.5 and 1. This was done with random forests that have 100 trees and a depth that is of 5 for each tree in the forest. We compared this approach with previous approaches, for example, the feature tweaking that I rapidly discussed earlier, a maze algorithm, which is based on different techniques for trying to search for an optimal explanation, and another mathematical model that existed that was called OAE, and that was able to deal with a number of different objective functions and also plausibility constraints. In order to compare everyone in a way that is fair, we use the same objective for all the models, okay? So we really use the same objective, same set of constraints, just, of course, different formulation depending on the technique that is used. And we even serialize the random forest to make sure that we are testing the same data points. This is the growth of the computational time. Sorry, I forgot something in the previous slide. So one thing that struck us was really the quality of the solution produced by the method. This is not a gap, this is a ratio between the distances. So in the OR community, this would be like a 3,100% gap of optimality of the feature tweaking algorithm. The maze algorithm, it is not 100% optimal because it has some precision threshold, but it's usually very close to an optimal explanation. And the OAE and Ocean, they are both based on mixed integral programming and they are both optimal. The only difference is that thanks to the good features of our model, like the sparsity, the number of integral variables, the CPU time is way smaller than other techniques for optimal explanations. The computational time is quite stable with the depth of the trees and also the number of trees. It grows, of course, but it doesn't grow out of control. I mean, we arrive to 30 seconds in cases that are with a much larger depth, for example, 8, or with a much larger number of trees, 500. We tested maze on OAE in some cases, for example, with 500 trees, and it could easily reach 5 hours. It's quite a common thing in optimum solution methods and mixed integral program. When it fails, well, it fails. It's just too slow to reach anything meaningful. And one last thing that we did, which is an extension of the model, which I believe has a lot of potential, is to have a more sophisticated definition of what is a plausible domain for search and explanation. So let me just kind of look at this figure for you. This is the initial point for the explanation. And this is the random forest behavior. You can see it has a kind of decision function that is a bit like this. Okay. A bit like that. If you don't constrain the explanation to be plausible, the first thing that your model will do is to find this explanation here. It will tell you, well, great, according to your model, this gives you the right class. So this is the explanation for your question. This is what you need to do to get your credit. However, going from here to here, it's very unlikely to happen. The reason is that this data point here in red that I've put, it is totally out of the distribution of the usual red data points. So it is a clear outlier of the rest of the distribution of the points. It doesn't constitute a meaningful explanation for anyone. If you want a meaningful explanation, you have to remain within the plausibility region of the counterfactual explanation of the distribution of the target class. So if I look, for example, at this region that is kind of delimiting the set of good cases of this class, then I have interest actually of finding the closest counterfactual explanation that belongs to this set. Okay. Now the question is how we can efficiently represent this set. Very often you get sets that are plausible, that are not convex, that correspond to disjunctions, that are not very easy to represent. However, in the literature, there is something that's called isolation forest. Isolation forest is a technique that is designed to characterize outliers. It consists in training a set of random trees. So you are not creating a random forest now. You are creating a random split everywhere on a random subset of the data. And you will measure the average depths of a sample within this randomized forest. And the assumption is that samples that have a shallow depths in the randomized forest, they tend to be outliers because they are very quickly kind of isolated by some of the random splits. And in practice, this works super well. This is a very efficient way of characterizing outliers. You can see in this figure, the shaded area actually is the domain of plausible samples as determined by an isolation forest. The other good thing with isolation forest is that, well, they are forests. So we can use exactly the same model as we use for the random forest, but this time to characterize and constrain plausibility. So the test that we did was to take our model for random forest, just add an additional set of constraints that correspond to the isolation forest and see how it goes. And indeed, we get those optimal counterfactual explanation now restricted to a plausibility region. And we get computational time that are still very tractable. Compared to the original algorithm, it is a matter of 2 or 3 times the usual computational time. So the plausibility was gained at the cost of a bit more computational effort, but it was not dramatic. Okay, so this is another domain where I believe that mixed integral programming, combinatorial optimization has a very important part to play. Clearly, the instability of heuristic explanation is not something that is suitable for critical application. We'll need something that is grounded on some real guarantees, some real mathematical definition on models that are solved to optimality. I really suggest you to explore a bit this domain if you're interested. There is certainly a very large number of open research perspectives in this domain, to generalize to different types of classifiers, to include other consideration, fairness, robustness, things like that. There is really, really good potential here. Okay, that's the reference for this part. Great. What time is it? 9:34. Let's do 5-minute question. Do you want? Then I do the last part very quickly. How is in the chat? Okay, so, very good question. So, what if I try to compute first the bounding entry and then use it for counterfactual explanation? Well, the thing is that counterfactual explanation, they are a much simpler task than bounding tree. Actually, it's a subset of a bounding tree task, because when you try to calculate bounding tree, there is many steps in the method where you try to prove that a certain region is homogeneous. That is has no sample of the opposite class. So you can see counterfactual explanation as a routine that actually is used at many steps during the creation of a bounding tree. So the suggestion is really reversed. It's not that bounding tree should be used for counterfactual explanation, but more the other way around. At least if you want the bounding tree to maintain that guaranteed faithfulness. Thanks. That's really a great question. The optimal counterfactual explanation that really was a kind of spin-off of this line of research of bounding tree, and we really saw it as something that has a very good potential on its own after further analysis. But all of these are kind of pieces of a puzzle, or kind of set of methodologies that can be used for training, for explaining, for simplifying random forests. Okay, I will not lose too much time to just complete on time. I will briefly do the last part of this presentation about another application of mixed integral programming. Now it's really a training task. So we are going to do optimal training, and we are going to do that for decision diagrams. So let me show you how it looks like. If you have been a bit tuned with the last American election, you probably have seen all these nice figures and graphs that look at the different scenarios, Pennsylvania and whatever could happen for this election, and what are the scenarios that can lead to a Biden win, to a Trump, or to a tie. And very often we saw in this analysis that these analyses that were very conveniently represented as a decision diagram. So a decision diagram is a set of tests, yes, no, a bit like a decision tree, that leads to a final classification. The only difference with the decision tree is that there is possible joint operations that are occurring at different steps of the classification. So for example, I can obtain that node from different paths. I can either pass through this node or this node, for example, and that's going to be different outcomes. As soon as we are on this node, it will lead to the same process after that. So if you had to represent this decision diagram as a tree, you will have something that's very extensive, and that will be very difficult to comprehend. If you look at the diagram itself, it's way simpler than the decision tree. So you kind of wonder, well, decision trees, they are so popular in machine learning. Is there a reason why we always train decision tree, but we never really train decision diagrams for classification? So that's the question that we have raised, on that with our co-authors, we decided to explore from a mixed integral programming perspective. So decision diagrams have been really used in many domains: logic synthesis, circuit verification, optimization, artificial intelligence, and so on. It's just that training them as a classification model, not very common. Why this is so? There is a lot of advantages for decision diagrams. First, their depth is not bound to always grow exponentially with depth. So that means that you can make decision diagrams that are very, very deep, but very thin somehow. In addition, you have complete freedom in the design of the topology within the decision diagram. So we will consider that the topology, that is the connection that has internal inside the diagram, they are supposed to be done at the training stage. They are not fixed in advance. They are really done during training. On that, allow you to express a number of concepts that are more sophisticated. Like, for example, if you want to express a sequence of XORs, you are much better off with a decision diagram than with a decision tree. Actually, you will have a representation of this concept that is linear in terms of the size of the XOR expression, whether in a decision tree, you will have an exponential sign. But the very big drawback is that if you look at classical techniques for training decision trees, they don't extend very well to decision diagrams. They are very good at splitting, but they are very bad at topology optimization, merging, and things like that. So our goal was to propose the first generation of training algorithm based on mixed integer linear programming. This is a work that has been done recently. We have submitted it to a conference, and we will be soon providing the archive report for you. So let's see how it goes. Again, some mathematical programming things. I will not really dig into too much details here because we are running late on the seminar, and I want to leave time for the questions. But you can decompose really the model for training decision diagrams into different set of constraints that each represent a critical part of the behavior of this model. What we did first was to, well, now we have multiple samples because this is a training task. So I have to look at different samples. And for every sample, I need to understand how is the flow of this sample through the diagram. Okay. And the flow of the sample through the diagram is basically characterized by two decisions. The first is what happens on the splitting hyperplanes. Those go left and right. And this is basically the green edge that I put here. And there is another thing that occurs with the samples is once it goes left or right, depending on how I created the topology of my diagram, depending if I put a design arc to go from here to here, here, or here, I could end up in different places. So the efficient way that we found to represent these two interacting effects was to see the flow of the samples as a kind of flow within a network, except that after choosing left or right, there is an additional division that occurs, which could lead you to the different nodes depending on your topological design decisions. Okay, and well, to maintain the analogy with the diagram, we didn't really call these nodes real nodes of the diagram. They are just like splitting points that allow you to track the flow of the samples and to kind of establish a flow conservation. So let me come back to this. We have two types of flow variables. We have the flow variable for every sample I on every node U that are on the minus and plus side on that take value 1 if the sample exits on the left side or the right side of the hyperplane at this node. And then we have flow variables that connect the outcome, the positive and negative outcome of each node U to every node V of the next layer. An important thing as well, we added possibly arcs that go directly to the terminal nodes. This is also subject to optimization, and the topology can choose to do that. It's just that we don't represent it in this figure because they are just too numerous and it will be very, very difficult to read. Okay, so flow conservation of the sample in the diagram. Second thing, branching choices. Again, we use these lambda variables that tell you whether the sample will go left or right on this layer, and we connect these variables with the W variable. easy, and also good thing, you can relax the integrality of the W and just put the integrality on the lambda. It's basically, it's the same as profiting from the tree structure to make a kind of special order set constraint on the model. And then we have this topology decision. So for every intermediate node here, I need to select where this node will point. And we do that through additional Y variables that basically are the design variable that tell you whether this arc is open or not, on whether it can or not carry the Z flow. So these are the design variable Y. And we also add a D variable that tells you whether a node is open or not. Because sometimes for matter of sparsity, you want the optimization to be able to not exploit all the possible nodes of a decision diagram, but use a smaller subset. And this will be actually benefited in objective function. If you don't use many nodes, then this is profitable for you. And then there is a number of symmetry breaking constraints because there is different source of symmetry here. The first symmetry that occurs is due to reversals. So if you just take the hyperplane and you just shift it, instead of representing it like that, you represented it like that, then basically the sample, they would just switch ways. Or everything that was going to the left will go to the right, and everything to the right will go to the left. And then you would get an identical solution by doing this instead of this. So this is really bad because you have a kind of two possible ways for every node. You really want to break this symmetry. The way of doing that was basically to impose, let me remember, the left side always has to be on the left of the right side. So basically, if I have something going out here and something going out here, then this node needs to be located on the left of this node. So basically, we break symmetry directly on the design variable, not on the hyperplane coefficient. We found that to be stronger. Okay, and there is other symmetry breaking. I don't want to spend too much time on that. The objective function, it optimizes the classification accuracy, and it has a term to optimize sparsity. That means you penalize you from using a lot of nodes into the decision diagram. Now let's go to the training method. We have 3 steps for training. The first step of the training is to do some form of heuristic construction in which we do a very similar thing as a CART algorithm for decision tree, except that instead of just splitting based on information gain criterion, we also need to choose where the result of the split will go. So for example, I have chosen the split. This leads me to basically 6 flows from these 3 nodes. But on the next nodes, on the next layer, I have only, let's say, 4 nodes available. Then I have to choose which one will go together. And this is what we call the merge operation. And we did that with something that is very greedy. We will merge the flow of samples in such a way that the information loss due to the merging is minimized. And to obtain better initial solution, we repeat that several times with different subset of the features at each split. And we also apply a very small local improvement that consists of improving the level of the split from top to bottom without changing the international topology decision that came from the merging policy. Another thing that is not noticeable in this first step is that there is not the possibility at this first step to directly go to a terminal node. These kind of long arcs that I mentioned a bit earlier, they are not used in the first step. And also the first step, it chooses the full width of the decision diagram that is available. So it doesn't optimize sparsity at all in the beginning. And then we use ways to improve that. The first thing is that we use a MILP that is focusing on each node separately. So we fix all decisions that do not relate to that node. For example, samples that do not go to this node, they're not considered in the model. every other choice of topology or hyperplane that is not in this node is fixed. And we can therefore write a MILP that is very compact and that optimizes the splitting hyperplane on the topology decision for that specific node. We run every node for 20 seconds in GoDoB in order to improve this initial solution. And finally, we run GoDoB on the entire MILP in order to have a very good decision diagram. So here is how it works in terms of experimental setup. We use the same data set as Bertsimas and Dan from their classical paper about optimal classification trees, because they are a very good variety of data sets and they are of different sizes. And they all come from the UCI machine learning repository. They have between 47 to 6,000 data points on 2 to more than 400 features. We will do two phases in the experiment. We will have a kind of training and then validation in order to calibrate some parameters and a final test stage. Let me explain how it works. So the first thing that we do is that we'll just use the training on validation sets. And the important thing that we want to calibrate for the decision diagrams is the weight of the regularization term. So the regularization term is the term that penalizes the opening nodes in the decision diagram. And we have chosen to try, for example, 5 different values. And we also look at the skeleton of the decision diagram, that is the number of nodes that are allowed per layer as a form of hyperparameter. Basically, the original skeleton and configuration of the decision diagram can take 4 different values. 1, 2, 4, 8, which is actually a decision tree topology, except that you can possibly deactivate some node and still are allowed to merge within it. The 1, 2, 4, 4, 4, which is kind of already something a little bit thinner. The 1, 2, 3, 3, 3, 3, and then the 1, 2, 2, 2, 2, 2, 2. That is a very, very thin decision diagram in which the sample, they go from top to bottom. Every layer has only 2 nodes at most, but don't forget one thing. If there is one side that want to send directly to a terminal node, it can do so. So progressively, the layers, they kind of exhaust the cases that are the most obvious, and they lead you to work on the remaining sample as you go down. Okay, and we train and measure the performance of these different configurations. The first thing that we wanted to see is whether we can actually solve the models. Is it really realistic to think that we can optimally train optimal decision diagrams in this way? The good news is, well, not so bad. With the data set that we considered, we were able to do optimal decision diagram training for roughly half of the data sets and the random seeds that we used. So that's quite a good news. And in the other case, even if you don't have the optimal solution of the third stage, you still have the first 2 stages that have been done. So you already have a good design for the decision diagram. Just cannot prove that it's a global optimum. In terms of number of samples and number of features, here is a very quick map that illustrates which optimal decision diagrams can be trained. When it's the round, it's solved to optimality. When it's across, it's not solved to optimality. See, here we have even this larger case with more than 400 features, we actually succeeded into training it. Or GoDoB succeeded. Sensitivity to regularization. We were really wondering what would be good design. Should we really go with decision diagrams that are very thin as the basic skeleton or not? And what is a good regularization parameter? Are we within a good range? Does it have a really big impact? So we use the validation set to compare the performance of the different models in terms of accuracy on the validation set. And we observed that in general, well, the first 3 skeletons were the most successful. Contrary to our initial intuition, this idea of mounting something extremely thin was not really profitable for the classification. In terms of alpha, sometimes you get good performance without any regularization, which is a bit surprising, but can happen in some cases. because there is very highly structured data set for in some of those cases. And sometimes you really benefit from penalizing heavily the use of the nodes of the decision diagram. That's the main tendency. In the middle, of course, you have a bit more distribution of alpha configuration that were the best. This basically counts how many times this skeleton on alpha was the best among all configurations. And finally, the last analysis that we did was, well, now we have done the validation. So we know for each data set what is a good value of alpha on the skeleton. Now we are going to look at our test set, which is a set that for now I have never used. So there is no data contamination. It's the first time that we discovered this new data set. And we are going to use the optimal decision diagrams with their best hyperparameter that has been found during validation, and compare them with optimal decision trees in the same sense as Bert-Simas and co-authors, also calibrated with hyperparameter tuning for the regularization coefficient alpha. And now we really want the race for the, let's say, state of the art in terms of accuracy. Do we really have a gain in using more sophisticated model like decision diagrams? And this is basically the accuracy of our model. You can see that we have much less occurrences of outliers with low performance and low accuracy, and we are consistently better in terms of accuracy. This is confirmed by Wilcoxon test between the two sets of results. We can also represent the cumulative distribution of the test accuracy over all instances. When you get a graph like this, if you're on top of another method, this means that you are consistently finding better results. Another thing that is very interesting is to look at how the data passes through optimal decision trees and optimal decision diagrams. So this is an optimal decision tree. And one thing that is striking is that it's very common in optimal decision trees to have nodes that contain very few samples. It's something that is very well known because when you have a decision tree, it gets wider and wider. So in proportion, the number of samples that passes through a layer, especially down, it becomes very small. So the last layer have a heavy tendency to overfill the data. When you look at the decision diagram, since you are controlling the number of nodes in each layer, you are actually exploiting fully every node that belongs to the decision diagram to do the classification. So you don't see very much that kind of cases where you have a node that is activated, but that is actually useful for very little data. Okay, so that was the experiment that we have so far. That was the surface of mixed integral programming for something that relates to explainable AI, because we are training classifiers that are more compact, they are more sparse, they are more, sometimes a bit more useful to look at and do the interpretation. Again, this is a case where as OR practitioners, experts in mixed integral programming, we can contribute largely to the domain. And I think that there is a large number of possible research paths in this domain. General conclusions, a lot of possibilities related to the intersection of OR and interpretable ML. In this work, we have heavily focused on random forests and this kind of methods because they have really combinatorial structure. So it's really our type of playground. If we go to neural networks, the models becomes much more intricate. Also, we would need to very often deal with nonlinear behaviors. So that's another challenging area that is vastly unexplored, but very difficult. And there is still progress to do on many of these aspects. I don't want to keep you too much time because we have reached the end of this seminar. I let the microphone open so that we can exchange a bit and have some final questions. Thank you so much for participating to this seminar. It was great to have you. And I'm available for questions. Last thing that I should not mention, since the scale I share is starting in Polytechnic, There will be a lot of positions related either to the master level, doctorate level, and postdoc. If you have some interest related to these topics, just drop me an email and there may be some opportunities. If you want to find source code, just follow, and also Twitter. I post updates on research topics, new papers very regularly. Thank you, and bye. On questions.
Thank you very much. Thank you very much, Thibaut, for these great talks. And is there any question?
Thank you, Clarisse and Nadia, for the words. The seminar duration was originally 2 hours, so I understand if people have to go. I will stay online in any case for the next 10 minutes to have discussion question with whoever wants to chat or have a coffee.
Okay, just to mention that we are recording the presentation and that it will be available on the website where the conference was announced.
Mm-hmm.
Maybe I have one question.
Yes,
and if others have, please ask them. It's just about isn't the problem of the diagrams you are working on the fact that people don't use them because they look for something that look more simple? It's just, I mean, it looks like they are not popular, and the reason is people are just have the habit of working with decision trees and don't want to use decision diagrams.
I don't know, they achieve better compression in a sense. You have much more compact models for the same performance. So they are really attractive. I think the only reason why people don't use them is really CART. Like CART is the usual way of training decision tree. Everybody knows in a textbook that you have to look at information gain or entropy or whatever. You can do the split this way. You know when you should stop because there is literature on that about what is a good post-pruning or stopping criterion for splitting. You have every resource needed to do that. If you look at decision diagrams, training decision diagrams is much more difficult. You have to split, but you have to merge. And very often, these merge, they can be quite misleading. Without some global optimization on top, you can have a pretty big performance gap. So from a heuristic viewpoint, from a construction viewpoint, getting an initial decision diagram is much more difficult. But there is a lot of potential. I think it's very funny. A good heuristic would really help a lot also. And generalize this into ensembles, that's also really promising. I've seen one paper that does forest of decision diagrams, to my knowledge.
Thanks. If people have questions, don't hesitate to unmute and ask your question.
Hi, Thibaut. Thank you for this tutorial. It was so interesting. Let me just put my video, unable to start video. Okay, because the host has stopped it. Okay. I can ask anyway. So my question is related to born again trees, which I found really fascinating. So, so first, like, are these trees? Are there any kind of uniqueness properties of these trees?
No, they are not unique necessarily, because if you optimize depth, you have many possible types. So you will find a large number of trees that are tying in terms of depth. And even if you use like a hierarchical objective that is depth first and then number of leaf seconds or reversely, you will still find equivalent solution. There's no way to avoid that. Also because sometimes data is symmetric. So when you have symmetry, you have a large number of symmetrical possible born-again trees.
Okay. And another question is, if these trees are equivalent to the random forest based on the same data, I'm wondering if it's possible to learn them, like if by any learning process you could reach this kind of trees.
So I just rephrase your question because they are not faithful for a given data, because they are not trained really based on the data. They are trained based on the structure of the forest. It's not dependent on some data points. I mean, if you take other points, it will also work. It will be the same. The thing is, when we train them, we must simultaneously create their structure and prove that there is no point that escape the behavior that you don't imitate perfectly. So there is a kind of optimization certification process that is going on. That's very interesting. You could design, you can really design actually some techniques that are based on sampling, where we start from a data set, we start creating some decision tree, and progressively we identify new points that are not classified correctly, and finally we manage to prove that we have exhausted everything and there is no behavior that is different. There is many ways to do that. I think there could be new development quite quickly about that.
Okay, thank you.
There is the first paper that was done by Breiman was 1990 something, and that was already called born again trees, but it was done only through sampling. So they were generating a subset of data points on training a new tree on that. So it could not provide that guarantee that the new tree that has been trained will behave the same on the data point, but we also extend the behavior to everything else. And that was the main difference of those two works.
Mm-hmm. Okay, thank you.
Maybe we have time to take one last question.
Mm-hmm.
That's
we have
the
a question
moment
from
if you have a
Jordan.
question.
Yes. In the chat, there is a question for Jordan Gonzalez. So Jordan is asking the following. He discovered the concept of decision diagram and didn't see why it would be more interpretable than decision trees. The merging process is not easy to explain, definitely. Yeah, indeed. So you can have a merging process that involve, for example, a pass on the left on one side and a different node with a pass on the right that merge in the same place. That's not that totally possible, not a problem at all. I also concur with the fact that decision diagrams, they are perhaps more complex sometimes to look at. But if you look, for example, at the election case, yeah. Well, if I represent that as a decision tree, you will not even able to fit it on the page. If you look at the decision diagram, you can still do some analysis. You are able to read it, you can see and picture it. So I would say that the interpretability in that case is not really an interpretability that derives from the structure, but something that occurs from a better ability to compress the rules. So you can see that as a more compact decision process. That's my view on that. So you can argue that it's not interpretable or it's interpretable or not, but one thing is sure, it is clearly more compact. Thanks for the question.
So thank you very much, Thibaut, for this great presentation. And I think we can stop there. And thanks again.
Thank you so much, Axel. Have a great day.
Thanks. Goodbye, everyone.
Bye.